solid state joining. Okay, so primarily our focus will be on the joining of metals. Joining of metals. So, what are the different ways by which the metals are joined? So I'll talk initially about the few approaches. You know, if uh, the metals either of the same type or the different types of the metals are to be joined, it is not about the material joining, which will have, like say, the cast iron and the plastic or the paper with the plastic like that, but we'll primarily be talking about the metals, joining of the metals. So for joining of the metals, what is most important thing is the metallurgical continuity. Metallurgical continuity. So there has to be, like, from one side to another, if there are two components to be joined, then there has to be a continuity of the metal from A to A if the same type, and this continuity should exist metallurgically. There should not be any presence of voids, or say some kind of the scale or oxide, or some kind of the chemical. If these are there, then wherever these are present, then metallurgical continuity will be absent. And if there is a metallurgical continuity, there will be continuity of the, like say, the grains or the uh, metallic structure, even at the interface or the weld joint zone. So this is the meaning of the metallurgical continuity is needed for proper performance of a joint which is made of metal. So if the metallurgical continuity exists, then you get the desired and the proper performance of the metallic components which are being joined. This performance may be in terms of the mechanical properties that you will be looking for, in terms of the tensile strength, fatigue strength, creep resistance, or the toughness, etc. There can be multiple things. Likewise, there can be performance you may be looking in terms of, like say, the corrosion behavior, the how good corrosion resistant a joint uh, is. So that will also be governed by the not just continuity but homogeneity of the metallurgical continuity. You need just for mechanical properties you may be needing the metallurgical continuity, but for corrosion performance maybe the homogeneity or uniformity of the metallurgical characteristics will be important. Okay, so how do we get this? How do we get the metallurgical continuity if the joint is to be made? What are the broad approaches that we have in our in our like say, whatever approaches have been developed for developing the for making the joints of the metals so far in the field of science and technology, if you say so. The broad approaches which are used for developing the joints of the metal, this simply includes, the first and foremost which is very common, is the fusion of the metallic components which are to be joined. Okay, this is one components which are to be joined. But this may not always be the best option. No, in certain situations this may be good, but this is also not a best option available for joining different metals. Okay, the second approach here is to do some kind of the deformation. So focus is not on the fusion, focus is not on the diffusion, but here it is on the deformation. This deformation of the metal to be joined, it may be at macro level, okay, where say you deform the metal by few or few millimeters, or sorry, few centimeters. So macro level deformation, or it can be micro level deformation. Here idea behind this is first to have the mechanical interlocking, say interlocking, and it is so good that the metallurgical continuity is facilitated through the diffusion and the metallurgical interactions when the two metals come very close. So metallic mechanical interlocking followed by the metallurgical transformations or reactions, so that those will be providing the metallurgical continuity. Okay, so the third approach here is what we use very commonly, like if we are not relying much on the fusion or the deformation, then let us go with the diffusion. So just clean the two metallic pieces perfectly, smoothen them and put at room temperature. If you don't have the facility for the high temperature, maybe for few months, so then after some time you may find that joint has been developed. So the diffusion, the only requirement is very smooth surface, okay, and free from impurities, primarily like say the oxides or the oil or the absorbed gases which are present at the surface. So this is the third approach, but there are a lot of problems because to smoothen the surface, then to facilitate the diffusion, it takes very long to develop a joint, so the productivity is limited through the diffusion approach. But indirectly the diffusion is present in most of the cases whenever either fusion or the deformation kind of thing or solid liquid joining approach is applied. So next one is the approach which comes in where you don't fuse the things, fuse the base metal, but you fuse the low melting point material and put that in between. So that is what we can call it as a solid liquid based joining. So it doesn't fall in any of the category if you see above, and the processes which fall in this category, say, so here what we do, we take the two components to be joined, okay, and between them you put the low melting point material here. So on the solidification you get the joint, but here is still the low melting point material. Let's say this is the base and here you have the low melting point material like this. So it is not just like filling up the gap, but some kind of the metallurgical interaction between the solid base metal and the molten low melting point filler metal takes place, and this metallurgical interaction leads to the formation of the intermetallic compounds. One, at the same time, some diffusion of the elements from the low melting point filler to the base metal, and from the base metal to the low melting point filler, which is there in form of shoulder or in form of the brazing metal. Okay, so the IMC formation and the diffusion across the interface, that will be dictating the joint performance. Okay, so the solid liquid based joining is the next approach. Lastly, about which we can say that is also very predominantly and the commonly used, that is about the chemical interaction based approach. So here what you use some kind of the chemicals, resins, hardeners, adhesives. So these interact with the surfaces, okay, but metallurgical continuity is not facilitated between the components. Here in brazing and soldering you have metallurgical continuity, but not so in case of the adhesive joining or where use resins and hardeners to develop the joint. Here some kind of the interaction between the adhesive and the base metal takes place, but metallurgical continuity is not developed across the interface. So this is one approach where there is no metallurgical continuity. Okay, so this is the one out of these say 4 5 approaches where there is no the chemical interaction based approach where you use adhesives. The metallurgical continuity is not established. Okay, so if you go further with the way by which these are working and the kind of joints which are developed, say whether you use the fusion or you use the deformation or you use the diffusion, and then what I said, solid liquid joining process, and lastly there was a chemical interaction based process. Okay, so since there is no metallurgical continuity, so this joint is very weak. It doesn't sustain very high the loads, the load carrying capacity of the chemical joints are very poor in terms of the load carrying capacity, fatigue performance, and thermal stability. So the first and foremost, you can say thermal stability of the chemical joint is very poor. The tensile and the fatigue load carrying capacity is poor. So these are not you can say not very good for structural developing the structural joints where good load carrying capacity is needed. The adhesives get thermally decomposed at elevated temperatures, so they do not perform really very well. So if the joint is non-load carrying type, it has to be used under the dry ambient condition, and the temperature condition is also not high, like say 40-50 is fine. So under those conditions, just and the role of the joint is just to ensure the proper placement or positioning of the two members being joined, then it is fine to use the adhesive joint. Okay, but these are not good for high load carrying capacity, and the primary reason behind this is absence of the metallurgical continuity in the joints. Okay, the next one is the solid state. This the brazing and the soldering kind of processes. These joints are also these are certainly stronger than the adhesive joint, but not as good as the simple fusion weld joint or deformation based joint or diffusion based joint developed using other three approaches. The reason behind this is what that is also to be seen. Since the brazing material and the soldering material, these are very low melting point as compared to the base metal. We always choose the brazing and soldering material in such a way that they are of the lower melting point than the base metal, which means they are of the lower strength. So they are good enough for to take the moderate load at moderate temperature, but certainly not the higher load and higher temperature. Okay, so these are good for moderate you can say the loading, and maybe purpose is just not to take the higher loads, but it is just to ensure the proper retention and positioning of the two members to be joined, or to facilitate the thermal conductivity or electrical conductivity between the two members which are to be joined. So the loading is not mechanical loading is not much say, but to facilitate the electrical or thermal connectivity, these may be good enough. So depending upon the application and situation, we may use the brazing soldering where there is no melting and fusion of the base metal. Little heat is supplied just to ensure the brazing, just to ensure the melting of the low melting point filler, which is used in form of the brazing and soldering. Okay, if we talk of let me see if I can erase some of the things. Okay, so if we talk of the brazing and sorry, the diffusion and what do you call the deformation and yeah, so the next is the diffusion. Most of the time, the diffusion bonding is carried out around zero point 0.5 to zero point 0.6 times of the melting point of the metal. So that's about above the recrystallization temperature of the metal. Tm is the melting point of the metal to be joined in Kelvin. Okay, so but here the problem here is uh, so there are certain things. The joint, let us talk about the joint first. So joint, since the process is entirely based on the diffusion across the interface. So diffusion of the atoms from metal A to the another member A, or it can be B. This can take place. The diffusion of atoms from one side to another is crucial for development of the bond at the interface. So if this to facilitate this diffusion, what atomic diffusion is important across the interface. So that you need to develop the suitable conditions for atomic diffusion to take place. And how that is possible, like you have to have very smooth surface across the smooth surfaces of the components to be joined, so that all these peaks and valleys are not able to have much of, they are not able to contribute much towards the gap between the two components to be joined. That's one. And then once the good contact is established between the two members, so when you apply load at especially at a high temperature during the bonding, these peaks and valleys get collapsed and good continuity is established between the two, but still diffusion may not take place. So you may have very smooth surface, you may have good temperature, but if the surfaces are contaminated with the oxide layer as small as like say few angstrom, or if there are say gases present at the surface, or oxides or the gases which are present, if these are there at the surface, then these are certainly going to hinder, obstruct the diffusion of the atoms across the interface. And if that is going to get hindered, then the certainly the continuity, metallic continuity will not be achieved 100%. There will always be some kind of the voids across the interface, which may be 5%, which may be 10%. So that those the voids and the you can say the porous zones will be contributing to the stress concentration, and thereby they will be deteriorating the joint performance. So in order to deal with these issues only, what we do, lot of innovative approaches are used, so that acceleration, diffusion can be accelerated, or not much smoothening of surface is needed, because that is very tedious task. So longer diffusion time and the poor very good surface preparation, these are the two bad aspects related with the diffusion bonding. So, and despite of all these things, if you have exposed entire component to be joined at high temperature, say in steels it is very common, like 800 to 900 degrees centigrade is very commonly used. So entire component will be exposed to the 800 to 900 degrees centigrade at high temperature for longer time. So everything is going to get softened, coarsened. So that is going to have the another side effect on the base metal performance itself. Okay, so there are two possibilities. Let's say this is this is the diffusion bonding interface. Okay, so if the both are the same component, both side you have the same metal, which is rare in case of the diffusion bonding, because we don't choose the diffusion bonding for joining the same metal. Mostly it is preferred for joining the dissimilar metals. Okay, so if that is the case, then high temperature exposure to the dissimilar metal component, this will have the differential effect on the two members. Even if it is the same, say A and A only, then high temperature exposure for longer time for diffusion to take place during the diffusion bonding, this is going to coarsen the structure. This is going to make the changes, many undesirable changes in the microstructure of the metal, and these things lead to the deterioration in the mechanical properties, compromise in the mechanical properties of the joint. So if I typically try to draw the hardness distribution across the interface, then in case of the perfect joint, certainly it will be there with a minor peak in the interface zone like this, and this is primarily attributed to the micro level deformation that will be occurring. Okay, but if we are using some kind of so if this is the case when we have the perfect joint. Okay, so on the other hand, if we have a joint diffusion bond where there are few voids, then certainly the joint strength is going to weak, and the hardness distribution will also be weaker as per the case. So if we draw a plot between the percentage of pores and the joint efficiency, joint efficiency is that what is the maximum load a joint can take place and what is the maximum load that base metal can take place. So diffusion bond strength of the you can say sigma u of the joint divided by sigma u of the base metal. So if this kind of the ratio is used to determine the joint efficiency. So obviously if there are pores, impurities or limited bonding in case of the diffusion bond, then the ultimate strength is going to be lesser than the base metal, and it may be like say 70%, it may be 80%, it may be 90%. So in general, increasing percentage of the pores or discontinuities at the interface reduces the strength of the joint. So here like say 10, 20, 30, 40 is a percentage of the porosity if you write, and the joint efficiency starting from say 100, 90, 80 or 70 like this. So you will find a decreasing trend. So joint efficiency will keep on decreasing with the increasing pores. So the point here is maximum you can gain for a good joint with free from the defects, no interlayers. You may have very close to the joint efficiency, maybe very close to the 100%, 96, 97, 98%. But if there are issues, there are porosities, there are discontinuities in the diffusion bonds, then the joint efficiency will be poor. That's one aspect. Second is like you started with the base metal which had say a strength of say 450 MPa in the beginning, both the sides. After the exposure at a high temperature of say 800 degrees centigrade for 2 hours, you may find that no, everything has changed. Now the structure has coarsened, the properties have, metallurgical properties have got modified. So now you will be left with the like say 400 MPa. So in general, the base metal property as a whole have been compromised. No, so which may not be acceptable from the design purpose or from the performance point of view. Okay, so that's the third approach where wherever the diffuser bonding is performed, if the joint is free from the discontinuities, you may get the joint strength as good as that of the base metal, otherwise it can be compromised significantly. The second is the base metal properties are also compromised. Okay, coming to the deformation. And now we are left with the two approaches, deformation and what you call fusion. Okay, so in case of the deformation and the fusion, the deformation, as I said, you just perform um, the joining in such a way that the micro level deformation at the interface takes place, like say in ultrasonic welding or your explosive welding. So here a micro level deformation leading to the mechanical interlocking, but here the intermingling and mixing of the metals from the two sides takes place to such an extent that metallurgical continuity is established across the interface. So this zone as a whole may be like say 2 to 4 micrometer only, but still the metallurgical continuity is developed. So diffusion coupled with the very good micro level mechanical deformation at the interface leading to the good metallurgical joint. The joint strength may be even higher than that of the base metal. So the joint is very good in this case, except that you need to have proper cleaning so that there is no impurity and what you call impurities and oxides present at the surface. So proper cleaning is needed. This is one case. The second case where we try to have the large scale deformation at the surface, at the edges of the members to be joined. So the member A, say same kind of the metal being joined using the solid state joining process. So forcefully you deform the metal in the control way, means edges of the components to be joined are deformed in controlled way so that the flow of the metal from one side to another takes place with the thorough mixing of the metal from one side to another, like this. So mixing and the large scale deformation, there are two things: large scale deformation, okay, proper mixing, and you can say the forging, because forging action. So these are three things in case of the large deformation based joining processes which are needed for defect free sound weld joint. Okay, and whenever it happens, you will notice that due to the deformation in general, the joint strength is higher than the base metal. Joint is stronger than the base metal. Now on the metal part I will come little later, but the thing is here, approach wise, if you see, whenever you deform any metal due to the work hardening, metal tends to get strengthened. Okay, but this the change in the strength, the change in properties may not be equal for all entire range of the metals. So on the metal part I will come little later. Let us talk about the deformation. So whenever the deformation is being real, if it is very limited deformation, then heat generation will also be limited due to the deformation or the friction. But whenever the deformation is of the large scale, it's very large in magnitude, then the heat will also be generated. So that heat will be leading to the changes in the properties of the base metal in the neighboring zone, leading to the formation of the heat affected zone. So the large scale deformation process, HHZ, is really a problem. Similarly, the deformation, weld zone or the weld nugget area may be stronger or it may be weaker. It depends, depending upon the metal system which is in consideration. But certainly most of the time good metallic continuity is realized. So because the way by which the properties will be changing in the fusion or in the deformation based approaches, they are to a great extent governed by the metal system, metal strengthening mechanisms, the way by which the particular metal has been designed, which is being joined. Okay, so on that I will come little later, maybe in today's lecture only. So heat affected zone and the weld nugget or the weld zone area, these are the two things. The weld nugget area is deformed and the heat affected zone area is will be experiencing the changes due to the frictional heat or the deformational heat which is introduced in the base metal during the weld joining itself. Okay, lastly here it is about the fusion. So the fusion, it's very simple one. Here the two components to be joined, so what you do, you in very control way you apply the heat. Okay, so idea here behind this approach is to have the controlled melting of the edges of the plates to be joined, edges of the member of the components to be joined, and subsequently so if they are of the same metal or the different metals, so they will be mixing with each other, and after the solidification they will be producing the weld joint. But for fusion to take place, you need a lot of heat input. A lot of heat is to be supplied, and heat is being supplied to the metals to be joined. Metals having good thermal conductivity, so they dissipate lot of heat to the underlying base metal, and this will be leading to the development of very wide heat affected zone both the sides. So depending upon the thermal conductivity, like say if you take the two metals of the different thermal conductivities, one is having very less thermal conductivity, so HAZ may be very narrow, and on the other hand thermal conductivity is high, so HAZ is also high. So that's what you can see here. So in one side little melting of the base metal is taking place, one, and the heat dissipated to the base metal is also narrow if the K is low. Alright. On the other hand, if the K is high, thermal conductivity is high, then you will find a lot of melting has taken place and a lot of heat has also dissipated, so leading to the wider HAZ. So HAZ width of HAZ will depend upon the thermal conductivity of the metal, apart from the heat being supplied and what you call preheating and other things. Okay, so in both the cases, solid state, in both the cases deformation based joining as well as in case of the fusion joining, where the problem is mainly related with the HAZ, that is most important, and then also in the weld nugget zone. Okay, or the weld zone or weld nugget zone or weld interface, you can say anything. Okay, so what are those problems and how to get where the problem is? Okay, so to understand that, we have to take a simple approach. You have developed a joint. There is a joint, you don't know how it has been developed. Okay, right, there is a joint, you don't know how it has been developed. So which is the weak area and where you should give the attention for improving the performance of joints. So there is a joint, you don't know how it has been developed. Now it needs improvement for improving the joint performance. So what we do, when we apply a tensile load to a joint, the joint can fail from three locations. The location one, the failure has occurred from the base metal one side itself, and the weld is intact like this. Okay, so in this case what we presume, like say A and B, and say this is weld, right? So A has failed, means your weld is strong and B is strong. So you see the base metal V is weak. This will simply suggest the second situation, that the failure is taking place not from the A and weld, but it is failing from the B side. So this will suggest that B is weak. These are the two things. Now if the failure is occurring from the, okay, let me erase this. Now if the failure is occurring from the, like say very close to the weld from A side, okay, like this, weld is here, right, and the other side is fine. So the B is strong, it is fine, the weld is fine, but the region next to the A, next to the weld on the A side, that is the HAZ, has failed. So HAZ is poor, means the HAZ properties are being very badly compromised, and you need to do something to restore the properties of the heat affected zone of the HAZ. Okay, And similarly, if the failure is occurring from the HZ of the B side, then you need to take care of the HZ of the B. Okay, so the weakness can be anywhere. Now lastly, to the weld. If the weld on application of the tensile loading, if it is failing from the weld zone, means we need to do something for the weld. It may be change of the filler, or it may be control of the defects, or something else has to be done in order to avoid the failure of the defects, failure of the weld. Okay, now coming to the factors that are governing the performance of a weld joint. So what we have to see is this. Okay, so performance of a weld joint being governed by the certain things. So there are, in a typical weld, there are these three zones: A, HZ, both the sides. I am not audible. Hello? Check your audio. No? Please check the audio. I think. Hello, Rajnish. Are you Rajnish? And who is not able to hear? Please check your audio. Check the connectivity or audio. I don't know. It is fine now. Can you hear me? Hello? Oh, okay. Now there is a HAZ. Okay. So as I said, the weakness can be there in the base metal, it can be there in the heat affected zone, or it can be there in the weld metal itself. Okay, so what are the things that are governing the weld performance? What are the things that are governing the HZ performance? Okay, so most of the time in welding people talk of the weld performance only. In solid state joining also you can have the weld zone, not typical to the fusion welding, but there is also a weld zone of this kind. It may be developed in solid state itself. You can have weld like this also, and it can also behave similar to that of the fusion weld joint. It's fine. So in a typical, say, in a typical fusion weld, what you have is there are two possibilities. One is there is a possibility to change the filler, or this is where we use the filler metal. But in autogeneous welding there is no choice. Or you know what is the autogeneous welding? Like the two edges of the plates are being joined without use of the filler metal. Okay, so say resistance welding is also an example of autogeneous welding. Friction welding is an also example of this autogeneous welding. Stick welding of thin sheet is usually performed in autogeneous mode because we don't use any filler. Okay, so if you have a choice of using filler, you can choose the filler of the higher strength so that the weld metal of greater strength can be made. Okay, so in this case there is no choice. But if you are using consumable kind of thing, consumable filler, then certainly at least you have choice to change the things. Okay, but if you talk of the weakness related with the heat affected zone, what you have in your hands for a given process, if you talk of the process you can use, like which are able to develop a weld joint with a 0.5 kilojoule per mm. You have the processes which will use the heat input of 1.5 kilojoule per mm, and there are processes which can use even 5 kilojoule per mm. So there are different category of the processes. More the heat you supply, greater will be the distance and greater will be the amount of changes that will be happening, greater will be the width of heat affected zone, greater will be the changes that will be happening. But Whether you use zero point 0.1 kilojoule or whether you use 5 kilojoule, in all these cases you cannot eliminate the heat affected zone, because heat will always be dissipated to the base metal whenever it is there. Now, the size of the heat affected zone, the width of heat affected zone can certainly be regulated, adjusted, controlled, and that is possible through the use of the suitable heat source. No, this may be true for laser and this is true for submerged arc welding. So depending upon the capability of the process, you can develop a weld with very low heat input or with the high heat input. So whenever the heat input is high, there is a greater tendency for the deterioration in the properties of the heat affected zone, and so the joint performance. This is very universal thing. The point is simple. The weld properties you can alter using suitable filler in case of the consumable processes, but you cannot do anything in case of the heat affected zone. Only thing that you can do is you can reduce HHZ related issues by reducing the heat input, and that option is very much available in case of the solid state joining, because comparatively either you don't supply any heat from outside or it is generated inherently during the process. So the solid state joining process, they will be developing the lesser heat, they will be the joints will be developed using the lesser heat, so HHZ problem may be very limited. Okay, and most of these joining processes, except when we use intentionally the filler, most of the solid state joining process, they are autogeneous only. Okay, and so the joint performance will be higher or will be lower or same as that of the base metal. This will depend the way by which the joint is responding to the deformation, or the base metals are responding to the deformation and heat generated during the joining itself. Okay, so the control of the heat affected zone is one thing and the weld is another thing. Okay, that option is available. So what are the things that will be governing and how to understand the kind of deterioration which is taking place in the heat affected zone, how to get idea of that, how to get idea of the kind of deterioration which is taking place and how far it is taking place. Say this is a weld. Okay, so what we do, we try to see that what is the kind of the temperature variation at a different distances from the fusion boundary or from the weld zone, say not in fusion boundary, in solid state joining, from the weld zone. So this is the weld zone area. So we put in different thermocouples and try to see the temperature variation as a function of time. And what we notice as a function of time, the temperature versus time relationship, like the zone which is very close to say 1, 2, 3, 4, the point which is very close to the weld nugget zone. So here you may find the variation in temperature like this. Okay, for the second location variation may be like this, for third location variation may be like this. So what is happening here, you just see this, the 0.4, 0.3, 0.2 and 0.1. The closest one is having, it is taking shorter time to reach to the peak temperature and the peak temperature is high. Okay, and high temperature retention is also for longer period. You take any particular temperature, you will find that high temperature retention is longer. So these are three things, and that is what is seen in terms of the cool heating rate, then soaking time and the cooling rate. These are three things which are seen with the help of these curves. So the point which is very close to the weld nugget area, this will be experiencing higher peak temperature for longer time, cooling rate is also high. Okay, But and all these things will be getting delayed. It is taking longer time. Further, it is taking longer time to reach peak temperature, and for the longer time, heating rate is also getting reduced. Cooling rates are also getting reduced. High soaking time is also getting reduced. So, depending upon the location uh, of interest in vicinity of the weld zone, the different temperature variations are experienced by the metal in the different zones, and that will be dictating the extent of the change which will be occurring in the region close to the weld zone. So since the temperature, peak temperature, high temperature retention time, and the cooling rates, all these things are getting affected with the location, and therefore you will find the changes are also different in the different locations. This may not be uniform. Okay, so this, what is the extent of a variation, that will depend upon the weld thermal cycle being experienced by the metal, and that you can quantify, that you can measure, and this will indicate the extent up to which the properties will get structure and properties will get modified in the heat affected zone. Okay, so so again, if you increase that heat input, your peak temperatures will change, cooling rates will change, heat input will this cooling rate, heating rate, and the peak temperatures, everything will get changed. So this may be for one heat input, say 1 kilojoule. If you go for 2 kilojoule, you may get the different weld thermal cycles. So accordingly, the metal will be affected in different way. The point here is, greater the heat input, it is very simple. Greater the heat input, more will be the problems related with the heat being given to the base metals. More will be the heat affected zone, more will be the deterioration in mechanical properties, greater will be the undesirable changes in the base metal which is being joined. Okay, so so these are the weld zone and the heat affected zone related things, and how do we try to understand that? I will plot one simple diagram, probably I have used it earlier somewhere. The heat input and the performance or the properties of the joint goes in like this. See, so if you initially increase the heat input, properties will go high, then they will start deteriorating like this. So there is an optimum value. When heat input is very low, you may find that joint is not developed properly. There are a lot of pores because of the very high cooling rate, lack of fusion, lack of penetration, or lack of proper mixing in solid state joining, etc. So here the discontinuities are there when the heat input is less, and there is a coarsening of the structure, deterioration in mechanical properties, deterioration in metallurgical properties, again will be compromising with the joint properties. So there is a need of the optimum heat input. Even this is true for many solid state joining processes. Okay, coming to the advantages of the solid state joining process. Maybe about this and many other things we will talk a little later. The thing is, there is no solidification related problems in solid state joining. You have seen they are mostly the deformation based or diffusion based or chemical process based. Okay, so there is no solidification related issues which may be in form of pores or inclusions or cracks, solidification cracks, etc. Usually the joint strength matching joint strength means the strength of the joint is matching with the base metal. That is what is realized. Okay, and another attractive part from the cost point of view, they don't use consumables. Means not in all the cases the consumables are used. In general, consumables are not used, but certainly fillers are used, interlayers are used in some of the cases. So the consumables in form of, like, say, shielding gases or filler fluxes, all these are not used. And there is a scope, since there is no metallurgical, not much in metallurgical interactions in the liquid state. So this feature allows the joining of the dissimilar metals. So dissimilar metal joining is possible through the solid state joining approaches. Okay, so advantages of SSJ, solid state joining. And the limitation related with this process is you need proper surface preparation. That is one thing, proper cleaning free from impurities, and in some cases proper edge preparation. Surfaces has to be properly straight and square. So edge preparation, you cannot say like it's a limitation, but you can say this is something which is to be done very carefully. And since the things are done in the solid state, so you need very robust and rigid machines. Robust machines are needed, because the joining has to be done using high power, high forces for deformation to facilitate, or even high temperature conditions in control environment like vacuum. So you need really the robust machines, and which are usually costly. Okay, so these, you can say, some of the plus and some of the, it is a not so plus or negative points. Okay, now coming to the in the solid state joining process, as I have said, there are three major things. SSJ, there are three major things. One is, as I said, the diffusion, and then deformation, and then you see adhesive process. Although in this case no metallurgical joint is made, but still it is solid state joining process. In case of the deformation and diffusion, the heat input is negligible or no heat input. Only little heat is given just for facilitating the curing in case of the adhesive joining. But there is a lot of heat supplied or generated internally in case of the deformation based joining processes to facilitate the deformation, as well as ensuring the mechanical interlocking. So the thing is, whenever metal is deformed or whenever it is heated, either using the external heat source like resistance or your induction or the friction, or it is in situ heating, like in situ conditions, you just apply the impact force, so kinetic energy is converted into the heat like an explosive welding. So similarly, the internal frictional heat is generated in case of the ultrasonic welding. So how about the response of the metals to these three things, to these two things? And these are mostly applicable for the deformation and diffusion based processes. So what about the response of the metals to the heat and to the deformation? This has to be seen with the care. It is not equal for all metals. So what we have here is like this. Let's have it. So what we'll get this way. Okay, how many corners I have got? One. Solid state, solid solution strengthening, grain refinement, precipitation hardening, work hardening, transformation hardening, and the dispersion hardening. So these are the 6 metal strengthening mechanisms. Okay, so if you see with respect to the heat which is being either supplied externally or it is being fed, or it is generated internally. So the metals which are strengthened by primarily the grain refinement, metals which are strengthened by precipitation hardening or by work hardening, and the transformation hardening, all these are very seriously or severely affected by the heat. So these you can say as heat sensitive metals, which will be affected to a greater extent by the heat being generated or being applied during the solid state joining. Certainly in the fusion joining the effect will be further more. Okay. On the other hand, the metals strengthened by the solid dissolution strengthening and the dispersion hardening, in these two cases the effect of heat is minor. It is there but not as much in case of the grain refinement, precipitation hardening, work hardening, and transformation hardening. Why? Because whatever the metal you are having, like dispersion hardening and the solid solution strengthening, in these two cases the strength is imparted by the presence of constituents like allying elements or reinforcing agent, and it is not expected that application of heat will change the things in any of the ways, except that minor grain coarsening can take place. So that may not be the significant factor for a metal strengthened by the solid solution strengthening or by the dispersion hardening. Similarly, the minor loss of the work hardening effect imparted during the manufacturing of those metallic sheets, that may also be neutralized. But since the metal is being strengthened by the grain refinement, dispersion hardening or by solid solution strengthening, so the loss of effect of work hardening or the loss of the properties due to the minor grain coarsening, that will be minor. Okay, so in these two cases the effect of heat is negligible. Second aspect is the deformation. You know, the most of the metals show work hardening behavior due to the strain hardening, but there is always huge relative ranking for that. Few get strengthened very heavily as compared to others, like aluminium doesn't get strengthened much due to the work hardening as compared to the, like, say, maybe take copper or a stainless steel or maybe cobalt. So there are few work hardening metals, they are designed for that. On the other hand, there few metals may show very weak work hardening behavior. So the way by which metal gets strengthened due to the deformation, due to the work hardening and strain hardening, that will dictate significantly the response of a particular metal to the solid state joining process.